And today we're gonna talk about non-ferrous metal separators.
Back, streets back, alright. Back, streets back, alright.
Let's start with the most important question. What exactly is a non-ferrous metal? The short answer is, it's a metal that doesn't contain iron.
They are generally more costly than ferrous metal. Non-ferrous metals are used because of their desirable properties, such as low weight, high conductivity, and non-magnetic property or even resistance to corrosion. Some non-ferrous metals are used in iron and steel industries.
Now, before we can further discuss about this topic, we first need to know the fundamental about the concept of electromagnetic induction. Electromagnetic induction is a process by which a current can be induced to flow due to a changing magnetic field, or changing the strength of the magnetic field over time can cause a current to flow. Okay, this is a simple example of the electromagnetic induction. As you can see, this is a circuit with a wire here, and this is a magnet. If you move the magnet into the solenoid, it will induce a current flow such that the current flow will produce a magnetic field which opposes the motion of the magnet. But yes, that is very confusing. But that's how it is. And if you pull the magnet out, what do you think it will happen? Remember that Lenz's law is about opposing the motion. So
Think about it.
think about it.
Simply put, electromagnetic induction is the production of an electromotive force across an electrical conductor in a ever-changing magnetic field. So in this picture, I have a question to ask you. Will the speed of the magnet that goes through the solenoid, what will happen to the induced current? Think about it.
Think about it.
Hi, welcome back. So, the answer is, the faster the magnet enters the solenoid, it results into a higher and stronger induced current for the entire circuit.
Now you understand the basics of electromagnetic induction. Finally, we can get into our today's topic. What are non-ferrous metal separators and how do they work? I will leave it to you, Jia. Oh, okay. So, non-ferrous metal separator, also known as eddy current separator, is an advanced separator that excellently separates non-ferrous metal such as aluminium, copper, and brass from inert materials such as glass, wood, and plastics, and then eliminate the smallest part of the ferrous metals left from the sorting with magnetic separator. It gives a great benefits because you can have all these three different types of materials sorted and downloaded directly into three separate containers. But why is it called eddy current separator? Why? Think about it.
Think about it.
Now, before we talk about eddy current, we must have a short revision on Faraday's law and Lenz's law. Tell them, Daniel.
Hello, I'll be explaining to you about Faraday's law. Now, Faraday's law states that the rate of change of flux linkage with respect to time is directly proportional to the induced EMF in a conductor or in a coil. it basically means that any change in the magnetic environment of a coil or a solenoid will cause a voltage, electromotive force, to be induced in the coil. Alright, so in this slide, I'll be talking about transformers. What's a role? What? Okay, let me talk to you about the working principle of a transformer. Say you have a wound of wire being coiled up on one side of a soft iron core, and induced current is being supplied by an alternating electrical source. The alternating current through the winding produces a continually changing magnetic flux, or an alternating magnetic flux, that surrounds the winding. If any other winding is brought nearer to the previous winding, obviously some portion of this magnetic flux will link with the second winding. So as this flux is continually changing in its amplitude and direction, there must be a change in the magnetic flux linkage in the second winding or the second coil on the other side of the transformer. Now, according to Faraday's law of electromagnetic induction, there must be an EMF induced in the second coil. If the circuit of the later winding is closed, there must be a current flowing through it. This is the simplest form of electrical power transformer, and this is the most basic of working principles of transformers. Alright, in reality, the electrical energy is not all conserved. A lot of it is converted into heat by eddy currents. In a transformer, the magnetic flux created by the primary coil induces a current in the transformer's core. This occurs in order to oppose the charge that produces the magnetic flux, which is Lenz's law. The currents flowing in the core are called eddy currents, and these currents produce heat, which use up energy and as a result causes inefficiency in the transformer. Alright, right now I'll be talking to you about Lenz's law. Lenz's law states that when an electromotive force is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. In layman's terms, an induced electromotive force always gives rise to a current whose magnetic field opposes the change in original magnetic flux. Alright, please ignore this sample text. This is a common example of a human error. Right, Lenz's law. When an EMF is generated by a change in magnetic flux according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. Now, the induced magnetic field inside any loop of wire or solenoid always acts to keep the magnetic flux in the loop constant. In the examples here, if the magnetic field is increasing, the induced field acts in opposition to it. And if it is decreasing, the induced field acts in the direction of the applied field, this way to the left, to try to keep it constant. You could use the right-hand grip rule to determine the polarity of the magnet, what's inside the solenoid.
Okay, now that you are ready, let's talk about eddy currents. This is a simple diagram. This is the conductor is moving from left to right with a velocity. This is a magnet. Since this is North Pole, the magnetic field will look like this. Eddy currents are loops of electrical currents induced within conductors by a changing magnetic field due to Faraday's law of induction. In this case, the conductor is moving across different magnetic field density. The changing magnetic field can be changed in strength of magnetic fields or the change in direction of magnetic field. As you can see, it has changed from north to south pole. Now, eddy currents induced will flow in closed loops within conductors in planes perpendicular to the magnetic field, which is something like this. By Lenz's law, the eddy current creates a magnetic field that opposes the change in the magnetic field that created it, which means eddy currents will react back on the source of the magnetic field.
Alright, now that we're all informed about eddy current, now let's get back into talking about non-ferrous metal separators, which are also known as eddy current separators. Eddy current separators work on the principle of varying action of eddy currents on materials with different electrical conductivity. These are the materials. Materials such as metals and non-metallic materials. See? Ferrous materials, for example steel, non-ferrous metals such as aluminum, and non-metallics such as glass and plastics all undergo the feeder and undergo the eddy current separation.
Magnetic induction rotating cylinders, which are these things, okay, are rapidly changing their magnetic field, which generates eddy current in metallic object present in the transported raw material. Okay, I'll explain again. So basically, this thing is magnetic field is keep changing. So when there's a metallic object passes through it, according to Faraday's law, EMF, or in this case, a current will be generated inside the metallic object, which is eddy current. So the eddy current generated will counteract the cause giving rise, which is stated in Lenz's law, if you can remember. So there's a repulsive force interaction between the metal object and the nearest magnetic pole induction rotor. So as a result, the metal particles are spouted from the conveyor belt. Here's another picture of the eddy current separator. So as you can see, the magnetic rotor is the spherical thing. Yeah, so it will keep changing its magnetic field. This will cause an eddy current to be induced inside the non-ferrous metal. The eddy current inside the non-ferrous metal will generate a magnetic field which will counteract the magnetic field from the magnetic rotor. This will ultimately cause the non-ferrous metal to be repelled away from the magnetic rotor. So now I will give you a quick rundown on the simulation and I'll explain as I go. As you can see, I put the ferrous metal inside the feeder. Oh wow, it attracts to the electromagnet. Amazing, now we try non-ferrous. Holy shit, just fly away. Like your money to the government. Oh my god, unbelievable. Uh, Apparently my teammate was not happy for my explanation. So I will redo a more serious version. I'm sorry, physics can ruin someone's mind. So now I'll be adding the ferrous material. Since it's ferrous and it contains iron, it will be attracted by the electromagnet, as so. Now I'll be putting non-ferrous material. Just like I explained, this should be spouted away from the rotor. Yup, just like I explained. Now, about non-metallics, for example, plastics, basically nothing will occur. It will just fall down here. Yeah.
Materials with a relatively low electrical conductivity. For example, imagine this as a material with a relatively low electrical conductivity. It is affected by the magnetic field of the rotor very little or not at all, and thus it will fall down by gravity to the end of the conveyor, just like this. As for the material of high electrical conductivity, just imagine this is the one with the high electrical conductivity. They are spouted from the conveyor to the different distance, depend mostly on the size of the object, the electrical conductivity, and the density of the material. For example, it will spout further away compared to the one with a low electrical conductivity.
Now you know how this thing works, but you must be wondering, what are the uses of eddy current separators?
Non-ferrous metal separators are often used in manufacturing factories that recycles waste materials after the fabrication of product in that industry.
Now, due to the mass fabrication of these products, oftentimes there are materials and particles that are often discarded and disposed as junk. However, eddy current separators aid as a recycling tool and also as a sorting tool where they take upon these particles and materials and sort them out into non-ferrous and ferrous metals in hopes to manage the waste that these factories carry out more efficiently and effectively.
Okay, guys, now I'll be talking about modification. Some of you must be wondering, why do you need to modify something that is so useful? Well, things that are useful does not mean it can be improved. The first modification I will be talking about is rotating crusher. The rotating crusher crushes big pieces to small pieces. As you can see, the big pieces at the top of the rotating crusher is bigger. As the process goes on, it becomes smaller and smaller, the pieces. It is for easier separation, and it will increase the efficiency.
Now, the next modification we can add is a wave sensor. It is able to detect the wave of the scrap or the material we will be using. So the speed of the motor will be adjusted automatically according to the wave. It will increase or decrease the repulsive force, meaning if the scrap is very heavy, the motor will go faster. If the metal is very small or not heavy, it will go slower. This will make sure a very light metal to not be propelled too far away, and a heavy metal not to be propelled too little. Here's a very realistic and accurate live action from me and my friends to demonstrate the modification.
Too fast, faster. This one nice, okay. Slower lah.
We interrupt this program to announce a very important message.
Alright, so for us to engage with the audience, we want to ask you guys, by now you should probably have realized that we've been changing our clothes, but if you haven't really realized, you guys should just wake up.
Guys, I'm sorry to inform you that Physics 800 Productions has ran out of budget, so I'll just use Paint as a explanation tool. Yes, I know, I'm sorry. It really ran out of budget already. Like those animations cost us like thousands of bucks. So yeah, it's not like we are lazy to find any other explanation tool. It's just that we run out of budget. Yeah, sorry. Now the next modification we can do is to add a cooling system to the separator. When eddy current repel the particles, they tend to heat up and dissipate their energy in heat form onto the particles. We could flow a cooling inert liquid, such as water, to cool off the separator. As you all know, water has a very high specific heat capacity. So now I'll demonstrate how the modification works. So you just add water, I think, here. So you can cool it down. That's it. So the next modification is vibrating conveyor belts. So this makes sure the distribution of materials is even and it's easier for the material to be repelled by the eddy current. So here's the example. Here you vibrate.
And voila, your material is now very dispersed.
That's it for us. The end.
Bye bye. Thanks for watching.
Think about it.